this session of organic chemistry videos, we will learn about alkynes, and we will talk about their nomenclature and preparation. Before we talk about the nomenclature of alkynes, we should remember the general structure of alkynes. Okay? Alkynes contain a carbon-carbon triple bond like this. Alkynes contain a carbon-carbon triple bond. And remember, please, that carbon-carbon triple bonds consist of 2 pi bonds and 1 sigma bond. The general nomenclature system, if you like, for the nomenclature of alkynes is this. So X dash alkyne. X dash alkyne. Alk is the root of the carbon chain containing the carbon-carbon triple bond. Ine reflects the functional group, or if you like, the family in this case, which is the alkyne family or functional group. So this part is the root, and this part is the family. This X, or this number, reflects the position of the carbon-carbon triple bond. So in order to apply this, if we are given a carbon chain containing a carbon-carbon triple bond, then we choose, as IUPAC will stipulate, we choose the longest continuous carbon chain containing the carbon-carbon triple bond. Step 2 would be to number the chain at the end closer to the carbon-carbon triple bond. Other rules, of course, apply with respect to the organization of the name that follows after that. So if we are given an example like this. For example, yeah? Okay, so we choose the longest continuous carbon chain. This is, of course, a simple linear compound containing a carbon-carbon triple bond. If we number the carbons, 1, 2, 3, 4, 5, 6, 7. So the longest continuous carbon chain now containing the carbon-carbon triple bond consists of seven carbons. Therefore, the alk part, if you like, or the root is 7. And therefore, if it is 7, then the alk part is hept. So therefore, it's hept and then ine. Hept ine to reflect the functional group that is present in this compound. So it's heptine, but also we need to specify the position of the carbon-carbon triple bond. That's why we need now to number the chain at the end closer to the carbon-carbon triple bond. Obviously, if we go from here, 1, 2, 3, 4, 5, 6, the carbon-carbon triple bond, we would get number 6. Alternatively, if we number from this end, then the carbon-carbon triple bond would get number 1. And of course, IUPAC rules favor a smaller set of numbers. Always, obviously, 1 is better than 6. So in this case, the name of the compound is 1-heptine. 1-heptine. We could also put the numbers. Okay, 1, 2, 3, 4, 5, 6, 7. So this is an alkyne of 7 carbons, therefore it is heptine. The position of the carbon-carbon triple bond is number 1. So that's why the IUPAC name of this alkyne is 1-heptine. What if compounds has more than 1 carbon-carbon triple bond? If they have more than 1, then they will be called diene. Di means still. Ine, of course, still the family of the alkyne functional group. So diene for compounds that contain 2 triple bonds. Compounds with 3 triple bonds should be named as trienes. Yeah. Okay. So if there are 2, let's say, triple bonds, 2 triple bonds, then the general name will be di, specifically if you like, okay, alk-a, diene, alk-a, diene, and of course this should be preceded by the positions of the 2 carbon-carbon triple bond. So X is the position of the first carbon-carbon triple bond in the chain, and Y is the position of the second carbon-carbon triple bond in the chain. Okay, so it's X, comma Y dash, if you like, alk-a, diene. If there are 3 triple bonds, then the alkyne will be named as generally triene, where then the more specific nomenclature system would be XYZ dash alk-a triene, XYZ alk-a triene, where X, Y, and Z are the positions of the 3 carbon-carbon triple bonds. Okay. There are compounds that contain different types of multiple bonds. For example, compounds that contain a carbon-carbon triple bond and a carbon-carbon double bond. So they are alkynes because they contain the carbon-carbon triple bond, and also they are considered alkenes because they contain a carbon-carbon double bond. So they are alkynes and alkenes, yeah? Okay, these compounds that contain both a carbon-carbon triple bond and a carbon-carbon double bond are generally termed as enines. So enines are compounds with a carbon-carbon double bond and a carbon-carbon triple bond. If you look at this general name, you would find out that the beginning is ene. So ene indicates that the compound is an alkene, basically, which means it contains a carbon-carbon double bond. So the carbon-carbon double bond is reflected in the ene part, this part here. It's an alkene. And this ine part is a result of the carbon-carbon triple bond. So it's ene and ine, but ene is quoted before ine. That's because alkenes get higher priority than alkynes. Alkenes get higher priority in general than alkynes. That's why it is ene-ine rather than ine-e. And also, if you notice, there is no e here after n, so it's not ene, and that's it, the end. No, it's ene-ine because it's not simply an alkene. It's alkene and alkyne at the same time, but since ene is written before, okay, and then ine after that, okay, then there shouldn't be an e after n because it's not yet the end of the general name. Let's take an example of a compound with a carbon-carbon double bond and a carbon-carbon triple bond. So this is a simple example. And if you look carefully, you will see that the compound consists or contains a carbon-carbon double bond and a carbon-carbon triple bond. And if you number the carbon atoms, you will find that it's 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 carbons in this chain, or in this E9 chain, if you like, or in this chain that contains the carbon-carbon double bond and the carbon-carbon triple bond. Now, the question would be, where do we number this chain? Because both multiple bonds are at positions 1. If you number from here, then the alkene would, or the carbon-carbon double bond would receive number 1. If you number from that end, the carbon-carbon triple bond would receive number 1. Well, in this case, the numbers will not be affected, okay, regardless of the numbering system. In other words, you get 1 always, so 1, 2, 3, 4, 5, 6, 7. You get always 1, 7 if you number from, let's say, left to right or from right to left. You get numbers 1 and 7. Always, whether you give 1 to the alkene or the carbon-carbon double bond, or you give 1 to the alkyne or the carbon-carbon triple bond. But since E9s get higher priority than alkenes, then the alkene also here will get a higher priority. In other words, if numbering from either end gives equal numbers, then alkenes get higher priority in the E9 numbering. And after that is the alkyne, which means the alkene here then receives number 1, and the alkyne receives number 7. So therefore, we should number from left to right rather than right to left. Alkenes get higher priority if numbering is the same from both ends. Alkenes get higher priority than alkynes in the nomenclature of E9. So 1, 2, 3, 4, 5, 6, 7, 8. So the carbon-carbon double bond is at position 1. The carbon-carbon triple bond is at position 7. And the root alk, if you like, alk is, remember, alk is the root. Alk is, in this case, is oct. So it's oct E9. So it's oct E9. But where do we put the numbers? Yeah. Okay. So the best way to do this is to follow this general nomenclature. So X dash alkene, X dash alkene. Ene denotes the possession of the carbon-carbon double bond in the chain. Alk is the root, and then dash Y dash ion. Alk is the root. This is the root of the chain. Ene reflects the carbon-carbon double bond, and ion reflects the carbon-carbon triple bond. And of course, X is the position of the carbon-carbon double bond, and Y is the position of the carbon-carbon triple bond. And if you notice again, there is no E here. This is very important, yeah? Okay, so there is no E in this case. There is no E after E. Okay, there is no E here after E, because it's not yet the end of the name. So the name of this compound is then 1 oct. 1 means that the alkene or the carbon-carbon double bond is at position number 1. The root is oct. Ene, yeah, the double bond is at position number 1 dash 7 dash I. 1 octene 7 ion is the IUPAC name of this carbon chain containing both a carbon-carbon double bond and the carbon-carbon triple bond. What if now the numbers are different? What if the locations of the carbon-carbon double bond and the carbon-carbon triple bonds are not at the termini, if you like, of the chain? So let's take an example. If we have something like that, something like this now. So we choose, now if we want to name the compound as an E9, we choose the longest continuous carbon chain containing both the carbon carbon-carbon double bond and the carbon-carbon triple bond. And to do that, then 1, 2, you could go up, down if you like, 1, 2, 3, 4, 5, 6, 7, 8 again. So 8 carbons is the longest chain containing both the carbon-carbon double bond and the carbon-carbon triple bond. But if you remember the chain from this end, 1, 2, 3, then the alkene would receive number 3, and then 4, 5, 6, 7. So 3 and 7 for the positions of the carbon-carbon double bond and the carbon-carbon triple bond respectively. 3 and 7. If you remember from that end, so 1 from the right end if you like, 1, 2, 3, 4, 5. So 1 and 5 is actually better than, let's put that, okay, so 1, let's write that down. So 1, 2, 3, 4, 5, 6, 7, 8. 1 and 5 are is a better set of numbers than say 3. If we write that down also like this: 1, 2, 3, 4, 5, 6, 7, 8. So 3 and 7 in the brown set of numbers is not as good as the red set of numbers, okay, which has 1 and 5. So therefore the red numbering system is preferred in this case. The red numbering system is preferred, but the general name, okay, will be followed, which means it's still an enine, of course, okay, that is not perturbed, okay, that's not changed, okay, regardless of having known or having learned that the numbering has to be done like this. So we maintain the same nomenclature system, but the numbers always, the smaller set of numbers are always, smaller sets of numbers are always targeted following IUPAC rules. So therefore the name of this compound would be, of course, if we number the chain like that, okay, then this would be a branch, an ethyl group at position number 6. So the name of this compound would be 6 ethyl, and then X dash alkene dash YI. So what's X? X is the position of the carbon-carbon double bond. So that X should be now 5. So 5 dash octene. So 6 ethyl 5 octene means the chain consists of 8 carbons. There is an ethyl group at carbon 6. There is a carbon-carbon double bond at position 5, but that's not yet the end of the name. We should continue with the ion part, then 1 ion, which means there is a carbon-carbon triple bond at position number 1. Okay, so this is the name of this compound. The point here is smaller sets of numbers are always targeted following IUPAC rules. If there is an option, or if you like, if numbering is the same from either end of the enine chain, then the alkene gets the higher priority than the alkyne. Having now learned about nomenclature, let's now talk about the preparation of alkynes. So in this section of the alkyne chapter, we will learn about the preparation of alkynes. So how can alkynes be made? Well, we learned before that alkenes compounds that contain carbon-carbon double bond can be prepared from alkyl halides. If alkyl halides are treated with a base, if you take an alkyl halide and you treat it with a base, then it is possible to obtain an alkene from it by a general reaction of elimination. The elimination reaction is specifically termed dehydrohalogenation. We learned that before when we talked about alkenes. So therefore, alkyl halides lose one molecule of HX in the elimination reaction in order to make an alkene. Now, what if we want to make a carbon-carbon triple bond. So we can imagine then loss of two molecules, if you like, of HX. So loss of two HX from a compound. And if that compound will lose 2 moles of HX, then the compound must have 2 halogens therefore. And that's exactly one method on how to make alkynes, and that is from compounds that contain 2 halogens. Compounds with 2 halogens are described as dihalides. So dihalides can lose 2 moles of HX to make an alkyne. Dihalides can lose 2 moles of HX to make an alkyne or to make a carbon-carbon triple bond. But a very important prerequisite is that the 2 halogens must be on adjacent carbons. They should not be on the same carbon, otherwise formation of the alkyne would not take place. So this is the general structure of the dihalide that should be suitable for the formation of an alkyne. It's a dihalide. You can term it as 1,2 dihalide. Okay, so this is a dihalide. Dihalide has 2 halogens on adjacent carbons, and each of these 2 carbons, not only they have 2 halogens, but also they have the necessary hydrogen to be lost in the reaction. Remember, it's dehydrohalogenation. It's actually double dehydrohalogenation in this case. So the dihalide will react, or should react, with a suitable base, and 1 mole of a base should be able to abstract 1 mole of hydrogen, if you like, or result in the loss of 1 mole of HX. And therefore, 2 moles of a base are needed here if 2 moles of HX are to be lost for the purpose of the formation of the alkyne. So the corresponding alkyne where a carbon-carbon triple bond between the 2 carbons that had the halogens now forms. This is the corresponding alkyne after loss of 2 moles of HX. So you can view this as double dehydrohalogenation reaction. Of course, it is an elimination reaction, so the reaction is elimination of elimination type. It is double dehydrohalogenation. Okay, this is briefly minus 2 HX. For that reason, then 2 moles of a base are needed. Examples of a base, okay, potassium hydroxide could be used. Of course, this is depending on the strength of the base, depending on the structure, obviously, but potassium hydroxide could be done, or could be used. Also, sodium amide could be used as well. This is even a stronger base. Remember, this is the amide ion. This is effectively the amide ion, and the amide ion comes from ammonia, and ammonia is a weak. Ammonia is a weak acid, of course, with a pKa of, as you can guess or remember, the pK of ammonia is 36. It's a very weak acid, and therefore this is a very strong base. This is a very strong base. This is a very weak acid. So a strong base is actually needed. The sodium amide or potassium amide is a strong base that is suitable for this double dehydrohalogenation reaction, or in the formation reaction, the alkyne formation reaction from the dihalide. Or potassium hydroxide as a amide base could also be used. So let me now give you 1 or 2 examples of this elimination reaction that results in the formation of alkynes. So this is now an example. a very simple example of a dibromide that can be used to make the corresponding alkyne. Remember, the carbon-carbon triple bond is always between the two carbons that have the two halogens which are lost. And if you remember also from before, this carbon has hydrogen, so the initial loss of the first mole of HX will be loss of X from one carbon and H from an adjacent carbon, almost like that, yeah? So, and the other mole of HX will be X from the other carbon and H from the adjacent carbons, like that, yeah? Okay, so loss of two moles of HX. Let's go back to this example. The product will be formation, or the corresponding alkyne, like that. Okay, so the carbon triple bond will be between these two carbons that have the two bromine atoms. Now, the first mole of sodium amide will result in loss of the first mole of HX. So if this Br and one H is lost using the first mole of sodium amide, then we will get this kind of intermediate after using 1 mole of sodium amide, or after the loss of the first mole of HX. This kind of intermediate is obtained. But loss of another, so here minus HX, okay, and this is minus the first HX, of course, 1 mole of sodium amide is used here, and the second mole is used here in the second step, if you like. This kind of intermediate contains a carbon-carbon double bond and X in general, bromo group in this case, yeah? It's described as vinyl halide. This is a vinyl halide compound, or vinyl bromide specifically in this case. It's thought of to be an intermediate in these types of reactions. So this is a vinyl halide or a vinyl bromide specifically in this case. So you can then limit the reaction to stop at the vinyl bromide stage or the vinyl halide stage if 1 mole of a base is actually used. Yeah, we can provide control in the reaction if we limit the amount of the reagent or the amount of the base that is used. So this is the one method on how to make alkynes, and that is to make them from dihalides by treatment of the dihalide with 2 moles of a suitable base. Vinyl halides are understood to be intermediates in this type of reaction.